this is a correction video for my previous solution to example 3.7.1. So here we have basically a kind of a square with a length of 1 in the reference configuration OABC that undergoes a displacement field as shown here, u1 equal to kx2 squared, u2 and u3 are 0. So in the first section, we're supposed to find the deform shape. So what we do, we have like 4 kind of elements in here: OA, AB, BC, and CO. So for the OA, we basically, so every point or every coordinate, on OA, it has an x2 equal to 0, x2 equal to 0. And since here x2 is equal to 0, then it will gives us basically u1, u2, and u3 remains 0. Therefore, OA remains the same, which means OA is equal to O prime, A prime. Let's say that this is the current or deformed configuration. So if we just plot this, this becomes O prime, A prime. And similarly, if I do this for CB, so every coordinate on CB, it has an x2 equal to 1. So if x2 is equal to 1, then that means that basically, let me write it here this way. So if I just put this down, then C prime, B prime equals to, so it becomes K, 0, and 0, which means that we have a translation in the x direction with the value of K. So let's call this as K. So these points become here C prime, and this points is K in here, and this becomes V prime. So it becomes like this. Now let's do this for A, B. So every point, every coordinate on, let's say CB, has a different, x2 value, where x2 it is between 0 and 1. Therefore, the A prime B prime becomes, so it becomes this displacement field in here, kx2, kx2 squared, 0 and 0. So you can see that this is changing non-linearly. So it's changing quadratically, so like this. And then again, every point on, let's say this is OC or CO, let's call it OC, it has a different, let me just copy and paste this from here. So he has a different value of x2. Therefore, O prime, C prime, again becomes kx2 squared, 0 and 0. So this is changing kx2 squared. So now we have our deformed shape. Next, actually question asks us to find the deformed vector in the reference configuration of dx1 equal to dx1 e1 and dx, let me write it here, and dx2 equal to dx2 e1 on point C. So the whole idea here, I changed my color. All right. So the whole idea here is we have to, let me just copy. Let me see if I can create another figure here. So the whole idea here is that we have two vectors, dx1 and dx2, and these are given to us. But suppose that these are not given to you. So what you do normally is you basically assume, you can assume infinite number of, vectors here on point C, on point B, or whatever that you have, and then you name them dx1, dx2, and dx3, and blah, blah, blah. And then what you do is you basically find the deformed configuration of these vectors, dx1 to dx whatever, and then you will find the kind of the deform, you basically find their kind of their angle here between their angle in the deform configuration. But here the whole idea is using two vectors which are basically orthogonal to each other, dx1, oops, dx, don't want to mess up with indices, and dx2. So these are orthogonal in the reference configuration, and we want to see how they change under this deformation in the reference configuration, in the current configuration. So that's why the book actually recommended using dx1 and dx2 in here. But you can take as long as any vector that you are comfortable with. We usually are comfortable with the kind of the vectors which are orthogonal to each other, like dx1 and dx2, capital X1 and X2, of course, and we continue with those. So here what we do is basically we have so now we want to get the kind of the deformed shape. So let me just go in here. So for dx1, which is this one, the dx1, the deformed vector in their reference configuration is dx1 plus dx1 plus del u dx1. So this equals to, and here we have del u. We have to find del u. So before doing that, I would like to just bring this del u in here. So del u, I think that I also made a mistake in here, so I corrected this one. So these are with respect to, previously they were with the reference configuration, which is incorrect. So they should be with respect to the reference configuration, not the current configuration. I hope that I made it clear. So they should be capital X. So these are not a small x. So if I just grab this in here, copy. All right, so now what I do is I have to take the partial derivatives of u1 with respect to capital X1, X2, and X3. So basically this becomes, it's going to be small. or let me just put it this way. So u1, it only has the kind of the derivative with respect to x2. So it's going to be 0, 2k, 2k x2, then 0, and all of these are going to be 0. So I just bring this in here, and for dx1, I have dx1 e1. So this is going to be dx1 0 0 plus del u, which is this one here, 0, 2k, 0, 0, 0, 0, 0, 0, and 0. Then I have dx1, 0, and then 0. So if I do this, then this becomes dx1, 0, and 0, plus, so this becomes 0, 0, 0, which means that basically dx1, it remains the same as we have in here. So they're basically the same. So dx1, so therefore dx1 is equal to dx1. So now let's do this for dx2. And I am doing this for point C, of course. This is for point C. And I will also do this for point B, just as a practice. So dx2 becomes dx capital del u dx2. For, again, what I have here, I tried to be somehow copy and paste this from here. All right, so since dx2 basically only has, dx2, it is dx2 e2, not e1. So this is going to be 0, dx2, this is going to be the same, this is going to be 0, and this is dx2. So this becomes 0, dx2, 0. And then what I have here, so this is going to be 2k dx2, and the rest are going to be 0. So this is going to be 2k dx2, dx2, and then 0. So as you can see in here, dx2, it has two components. It has 2k, 1 and 0, dx. This is like the kind of the magnitude. So, but previously for dx2, what we had was 0, 1, 0, and dx2. So if I compare these in here, so these were like, these are the initial one. So let me just make this clear. And if I just grab, this, copy, just paste in here. So now you can see that previously, sorry. So these were the same. So dx1 remains the same as dx1. So this is my deformed. Let's call it. This is my deformed shape. Let me do it by another color. So then this is C prime. So dx1 remains the same, but here dx2, you can see that the x component of dx2 in here is going to change. So here it becomes multiplied by 2 and then it becomes 1. So it becomes something like this. For we can get the magnitude of this, for example, I can just write it here. So the magnitude of dx1 is going to be, of course, 1, or let's say dx 1, and the magnitude of dx2 is going to be, so basically 4k squared plus 1 square root dx1. So now you can see that here we have an angle. We call this theta, right? So in the deform configuration, we can see that d capital X1 and d capital X2 are deformed to d small x1 and d small x2. And in the next section, we're going to somehow find this theta, which is the angle between dx1 and dx2. But let's do this for also point B. So again, similar to this, I would like to select two points, but this time, and again, of course, I would like to go with the kind of the dx1 and dx2, which are, of course, again, or, oh, I'm sorry, I have to put this in here, which are, of course, orthogonal to each other. So if I do the same, so dx1 is, of course, the capital X1 plus del u. And this is, of course, for point B, and this was for point C. Del u dx2, then dx1 is going to be basically dx1, 0, 0, plus del u was 2k, 0. And here, of course, we have 2k, and we also have like x2, but since here the x2 is 1, so it might be a good idea to say that this is for x21 equal to 1, and this is, of course, for x2 equal to 1. So 2k and 0, 0, 0, 0, all the rest. For x2, of course, equal to 1. Then I have dx1, 0, 0, which is equal to dx1, 0, 0, plus, oops, so this becomes again 0, 0, 0. So this becomes again dx1, 0, and 0. So if I again do this for, let me just write it again. So dx2, this becomes d capital X2 plus del u d capital X2 is equal to this is 0, dx2, right? Yes, e2. 0 plus, this is 0, 2k, 0, 0. And this is for x2 equal to 1 times 0, dx2, and then 0. This is equal to 0 dx2, 0 plus This is going to be 2k dx2, then 0, and then 0, which becomes finally 2k 1, 0 dx2. So again, you can see that here the dx1 is the same as dx1. And here you can see that dx2 is equal to 2k 1, 0 dx2 compared to dx2, which is basically, dx2, which is 0, 1, 0 dx2. And remember, these are very, very small. These are just elements. And this is it. So again, if I grab this, I paste this in here, and let me go another color. So what it becomes is this b prime, then again dx2 remains the same. It only translates. So dx1 only translates as it is shown in here. But this one not only translates, it also deforms. So this becomes dx2. And again, the same angle is theta. So, and all those kind of things in here are also applicable to point B. So now suppose we want to find, so let's determine theta. So the theta is the angle between the two vectors in the deformed configuration or the current configuration. So what we use is basically we have the dot product of the two vectors. So the cosine, so a dot b is equal to the magnitude of a and b, and then the cosine theta. So the cosine theta here is going to be the dot product of basically the, since we are doing this in the current configuration, the theta is going to be dx1 dot dx2 divided by their magnitude. Dx2. This is this is equal to, so their dot product is going to be, so since here this is going to be dx1, so this is going to be 2k. Let me just write it. So dx1 0 0 dot 2k, right? 1 dx 2, and this is going to be dx, sorry, 2. And this is going to be dx2. Yes, so dx2 and then 0. And then we have the magnitude, which is dx1. And then we have the square root of 4k squared plus 1 and dx2. Of course, here we have the magnitude, so I just get rid of this. Put 1 in here. Here we have the magnitude of dx2. And here we, of course, have the magnitude of dx1, which is 1 0 0. And it might be a good idea just to put these in absolute in here just to show that these are the magnitudes. So I hope that I corrected everything. So, all right. So, and then finally, if we get rid of these dx1 and dx2, the magnitude, then finally what we get is 2k divided by the square root of 4k 4k squared plus 1. So this is the angle between these two vectors in here and also in here. This is the theta. And now let's suppose that we want to, and so far here, k is basically a very it's a kind of a number, so we have no assumption here for k. But now let's suppose that you want to determine the theta basically for a very small deformation, for infinitesimal deformation. So what we do is basically so I think that this was basically the part C, let's say, I'm not sure yet, but I think that that is going to be part C. But anyway, the whole idea is to determine this theta for the infinitesimal strain. So now, assuming k is very small, is very small compared, is very small, and also k is also positive, so it should be positive. So what we do is basically we have a change from half pi, which is like from the 2 orthogonal. So now it becomes smaller. So what we can do is basically the cosine theta is equal to 2k divided by 4k squared plus 1. So what I can do, okay, so this wasn't good. So what I can do is basically I can use the Taylor expansion for this. Where, for example, 1 plus x squared, it can be 1 plus x half plus whatever. So what I have, then I can write this as 2k divided by 1 plus, so this becomes 4k squared divided by 2, which is 2k squared plus the rest. And since k is very small, I can just assume that this is 0, so this becomes 2k. So therefore, the cosine theta is approximately equal to 2k for the infinitesimal strain. So for k, very small to 1. Very small compared, it is very small. So it is way less than 1. So, and then what I can do is, since these were orthogonal, so this was previously half pi, so I can assume that this is going to be gamma, and then the cosine half pi, so the theta is going to be basically half pi minus gamma. Therefore, gamma is going to be half pi minus theta. Therefore, okay, I think that I made a mistake, sorry. So theta half pi, okay, sorry. The first one was correct. Theta is equal to half pi minus gamma. So therefore, cosine theta is going to be equal to cosine half pi minus gamma. So this becomes sine gamma, which is approximately equal to, oops, 2k. And since gamma is very, like we are working on the infinitesimal, or a small deformation, therefore sine gamma can be approximately equal to gamma. Therefore, gamma is going to be 2k, which means that if, let me just throw it in here. If I have like dx1 and dx2, two vectors which are orthogonal to each other, but in the deformed configuration, this is b prime, and this is going to be b. dx1, dx2. This change in here, this gamma, is going to be approximately 2k. This is like the physical interpretation of this in here. So the displacement is going to be as k, but this gamma here is, sorry, it's going to be k, but this change in the angle gamma is going to be 2k, approximately 2k, for the infinitesimal strain.